This presentation introduces a pilot project carried out in Croatia as part of the Circular DigiBuild initiative. The goal to use machine learning to reduce the number of sensors needed and the expert effort required to achieve smart, energy-efficient building operation. The work was developed at the Innovation Center Nikola Tesla in collaboration with the University of Zagreb, Faculty of Electrical Engineering and Computing. The pilot is based on a real, fully operational office building in Croatia. The building spans 13 floors with over 200 zones, each equipped with fan coil units. The devices responsible for heating and cooling individual spaces. In total, over 300 fan coil units are in operation. Calorimeter measurements are collected at the floor level to track how much thermal power is consumed on each floor, a key input for energy optimization. Over 5 years, the building has generated nearly 3 billion data points, all recorded at 1-minute intervals. Having data is only the starting point. To extract real value, accurate models are needed. They are the key enabler behind advanced control, demand response, digital twins, and fault detection. The results at this pilot site show what becomes possible when models are in place. Thermal energy use was reduced by up to 36%. Electrical energy consumption of the fan coil units dropped by up to 80%. Building operating costs fell by up to 26%. Beyond energy, the models also delivered measurable improvements in occupant comfort, reducing overheating and maintaining better thermal conditions throughout the day, with direct benefits for health and work productivity. Despite this potential, building accurate models remains a major bottleneck. Modeling typically consumes up to 80% of total development effort, relies heavily on manual domain knowledge, and drives up digitalization costs. This is the challenge the pilot directly addresses. Rather than constructing models manually for each building, the goal is to turn raw operational data into scalable models through a systematic, reproducible workflow. The Smart Building Operation System in this project was originally based on a dynamic thermal model for fan coil units, a rigorous approach spanning 10 pages of equations. A key input to this model is the return temperature sensor, measuring the medium leaving the coil. The sensor itself is not expensive, but installing it, integrating it into the building automation system, and running cabling to each of hundreds of fan coil units adds up quickly. These costs, installation, integration, and cabling, are what make replication across buildings significantly more expensive. Reducing these requirements without sacrificing accuracy is precisely what the pilot set out to achieve. The proposed alternative is a static model. The idea is straightforward. The thermal power of each fan coil unit is proportional to the difference between the medium inlet temperature and the room air temperature. The inlet temperature comes from the calorimeter already on the branch. The room temperature is measured by the digital controller already in every zone. No new sensors needed. What remains unknown is the proportionality coefficient, highlighted in red on this slide. Because fan speed is a discrete state, a separate coefficient is identified for each speed level. The key fact enabling this identification is that the sum of all fan coil unit powers on a branch must equal the power measured by the calorimeter on that branch. The first step toward the static model is data cleaning. Since the model assumes steady-state conditions, transient periods are removed first. Intervals when all fan coil units are switched off are also excluded. These periods carry no useful information about individual unit behavior. The remaining data removed consists mainly of sensor faults and unit operation anomalies. After cleaning, 10 to 15% of the original data remains. That might sound like very little, but 10 to 15% of nearly 3 billion measurements is still a very substantial data set to work with. Once cleaned, the data is separated into operating regimes. Conditions differ not only across fan speed levels, but also between seasons. Heating and cooling produce meaningfully different behavior. 2 additional regimes are introduced, one for heating, one for cooling. Combined with 3 fan speed levels, this gives 6 regimes per fan coil unit and 6 coefficients to identify per unit. Across hundreds of units, that is a large number of parameters, but the available data is more than sufficient to support it. This table shows how many data points fall into each of the 6 regimes for a sample of zones. The differences are striking. The cooling season dominates because during cooling, the temperature difference between the medium and the room air is smaller, so the fan coil units must run longer, generating more data. Notably, even regimes with just 3 or 6 data points are sufficient to identify the coefficient reliably. The method used for identification is physics-informed machine learning. The introduced constraints state that all coefficients must be non-negative and must increase monotonically with fan speed. This embeds domain knowledge directly into the learning process. Resulting model performance is given in the figures on this slide. On the left, a regression plot for a single floor. Each point has 2 coordinates, measurement and model output. The goal is for all points to lie as close as possible to the red line, a perfect prediction. The closer the scatter, the better the model. The fit here is very tight. On the right, the same analysis covers the entire building. R² measures how well the model explains the data. A value of 1 is a perfect fit. Across all zones in the building, R² sits between 0.96 and 0.98, a strong result that confirms the approach scales from a single floor to the whole building. Model error across the day is examined here. For context, standard static energy calculations typically assume a 10% loss factor as an engineering approximation. This model achieves a prediction error consistently within -2 to +2% across both heating and cooling throughout the full working day, 5 times more accurate than the conventional assumption, using only sensors already present in the building. A practical question: does this approach require years of historical data? The answer is no. Stationary data can be collected during normal operation with minimal control adjustments, simply holding each control action constant for a short interval, allowing the system to settle. No test campaign, no comfort disruption, usable data within weeks. The minimum requirements are modest: a central heat meter, zone air temperature sensors, and logged fan coil unit control signals. To conclude, this pilot demonstrates what a systematic, data-driven approach can deliver. By combining operational data, domain knowledge, and machine learning, accurate thermal models can be built for entire buildings, scalably and without heavy engineering effort for each new site. The key outcomes: scalability across building types, reduced digitalization costs, and faster model development. This directly addresses the bottleneck limiting wider adoption of smart building technologies through a pathway validated on real operational data. More information about the Circular DigiBuild project is available at the project website. Contact details for this pilot and the modeling methodology are shown on screen.